As you can see on this schematic, this is what I have currently at the radio itself. This is the first electrolytic capacitor that we have after rectifying tube, and this is second one, and this area over here is actually a pi filter, and this resistor is at the moment equivalent resistor that is replacing the whole radio at the moment, as I said, without any tubes. This is why I have measured the current, and at this point here we have 350 volts, and it was 2.5, 2.4 actually milliamps. That's approximately 145 kilo ohms. So I have replaced in this resistor here that value, and this is the coil that we have in radio in pi filter, and I've measured its inductance. It's 15 millihenries, and after I ran a simulation for this, I'll just run it again. There it is. So you can see here, for example, that at 100 Hertz, which is going to be an AC leftover after rectifying alternating current, there is approximately 12 dB gain. So by 12 dB, we're going to reduce the voltage of 100 Hertz. So that is good. That is quite okay. But I was interested if this capacitor here of 100 microfarads is actually gonna do better than a lower value of 16, which was originally in this radio. And I will put back 16, and I will run the simulation again. I can say that this capacitor here is not affecting how the pi filter behaves. So let's run the simulation again. Note that we're still at old simulation. It's showing 12 dB at 100 Hertz. Running it again, something has changed. Now we have 27 dB. So that is 27 dB of attenuation of 100 Hertz. So it's twice better. So obviously I have made a mistake by putting quite higher value of 100 microfarads instead of 16. I don't have 16 at the moment, but I will definitely replace it with some smaller capacitor that I have. And you can also note here there is resonance, which is of course normal. Let's get back to the schematic. We have capacitor, we have inductance connected here together. So yeah, they're gonna have a resonant frequency, and this is why we see it here, but it's over 1 kilohertz, and it's not affecting us. It's not point of our interest because we're dealing basically with 100 hertz. That is something that is coming out from after the tube. So yeah, let's put a lower value and see how that gonna affect this. And it's gonna be interesting to measure all of this with oscilloscope to see if AC component is gonna drop after I replace this capacitor C3, after I replaced 100 microfarad that I have placed there with a lower value. So let's test that in practice. Now, as I said, I'm interested in measuring AC component as a leftover here in DC part. That is a positive DC that is power supplying our radio. And I have connected oscilloscope at this point. So there it is. That is the point where our coil is and where we have output of DC. And this is the signal, how it looks. That's an AC component that is still present in our DC. So I'll just stop it for a moment to take a single sequence so we can do some approximate measurements here. So as we can see, at the moment, oscilloscope is set for 10 milliseconds per 1 square. So we can see as well what is the frequency of this signal. It's of course a bit disturbed by interference and a lot of noise that is coming from the outside. Everything is not grounded at the moment, so we can expect a noise like this. And as we can see here, it takes approximately one square here to get from one maximum to another. And as I said, a lot of other noise is present here. As you can see, somewhere is more than one, somewhere less than one, but approximately 100 hertz. So that is what we are expecting. And now we will try to calculate what is the average value of this AC component. So looking at millivolts here, so some average of maximum is at, let's say, 60 millivolts, and the lower value is somewhere around 75, because we have this small one here. Some are bigger, but somewhere around 75. So we can say about 15 millivolts. When we divide that by half, we get, for single period, we get 7, let's say about 7 millivolts. And to get effective value, we will divide that by square root of 2. So 7 millivolts divided by square root of 2. Oh, sorry. 7 divides by square root of 2. And we will get 4.9, if you can see here. Yeah, 4.9, about 5 millivolts. That is an effective value. And I have this voltage meter connected. It's oscillating, of course, because it's not intended to measure anything above 50 hertz, but approximately we can see that it's moving from a couple of millivolts to up to 5 millivolts approximately. So that is basically correct, and it's showing also what we see here on oscilloscope. So we can say that we have about 5 millivolts of AC present at this moment as it is. And what I'm doing next is removing this second electrolytic capacitor of 100 microfarads, replacing it with some of lower value, and we will see if that's gonna improve reducing our AC component. Now, as previously, I have paused the signal to be able to make a measurement, and I'm gonna position cursor approximately to some average of positive peak. Let's say it's somewhere around here. Some of them are above, some are below, so 34, 33, yeah, like 33 millivolts. And let's get down to the negative again, some approximation like here, that is 49. So in total that is like 15, 16 millivolts. So I'm very glad that that this replacement of capacitor with the lower value with these two in serial connection actually gave much better results for this rectifier. So I paid enough attention to the rectifier part. Now I will assemble the radio back, putting back all the tubes which I have checked. Filament is good in each tube, and I'll pull out the loudspeaker because it has attached audio transformer. I need it for this, and we'll see how actually this radio works.